In this video, I'll be talking about Lab 4, where we look at circuits. The purpose of this experiment is to predict the behavior of circuits with resistors in series and in parallel, measure the values of current and potential difference, and examine RC circuits and their behavior. When looking at circuits with resistors in series, we found that the loop rule holds true and that the equation for current can be used to find the resistance of a resistor. When looking at RC circuits, we found that increasing resistance increased the time it took to charge and discharge capacitors. We also found that in plotting the natural log of delta V over delta V initial versus time allows us to find RC, the time constant. Here are the physical principles we used. The loop and node rule were explored in experiment 1, which looked at resistors in series in a circuit. The resistance in series equation, as well as the first equation, delta V equals IR, were also used for this experiment. Experiment 3 made use of the first two equations to derive an equation relating the natural log of delta V over delta V initial and time to find RC, the time constant. In these experiments, the system is the circuit and all its components, and the surroundings is everything else. In experiment 1, we looked at the circuit on the right, with values listed there. My prediction for I1 and I2, I used the resistor in series equation to find that the overall resistance is 147 ohms. I then used I equals delta V over R, which is 3 divided by 147, which is 0.02 amps. In the online simulator, create the circuit to the right. How does the predicted current I1 and I2 compare with the lab values? The simulator also got a value of 0.02 amps, and they're the same. What happens when you reverse the connection to one of the ammeters? The current is now negative 0.02 amps, which is equal magnitude but opposite direction. What happens if you replace one of the ammeters with a voltmeter? The voltmeter reads 3 volts, and the ammeter now reads 0 amps. This is because adding the voltmeter makes the circuit open, so the ammeter receives no current. The voltmeter only reads the voltage from the battery, which is 3 volts. In a continuation of experiment 1, we measured the potential difference for each part of the path around the circuit shown to the right. From A to B, we found a potential difference of negative 3 volts. For C to D, it was 0.96 volts, and from E to F, it was 2.04 volts. And for the rest of the pathways, it was 0. We summed those to get the delta V round trip, which equals 0, which is what we expected. The current was still 0.02 amps, so the voltmeter did not affect the current because it has a very high resistance, so no current flowed through it. On the graph on the bottom right, it is a graph of the potential difference over the circuit. So from A to B, it increased to 3 volts. From B to C, it stayed constant. From C to D, it decreased 0.96 volts. From D to E, it stayed constant. And from E to F, it decreased 2.04 volts. And then for the rest of the circuit, it stayed constant at 0. When the voltmeter is connected across the 100 ohm resistor, the ammeter reading is 0.02A. When the voltmeter is replaced with an ammeter in parallel with the 100 ohm resistor, the current through the other ammeter increases from 0.02 to 0.06 amps. It increases because a new node has been created and more current flows through the ammeter because it has no resistance. Because the segment of current has decreased resistance, using the equation I equals delta V over R, we know current will increase. Here are my calculations for the resistance of the 47 ohm resistor. I got 48 ohms, and for the 100 ohm resistor, I got 102 ohms, both of which are pretty close. And then the resistance of the wire and the resistance of the ammeter were both 0. For experiment 2, we looked at a simple RC circuit showed on the right. It contained a battery, a resistor, and a capacitor of the values listed there. First, when using the 10 ohm bulb, when the battery was connected, the light turns on at its brightest, and as time goes on, the bulb dims and eventually goes out. At this point, the current in the wire is 0. Now the capacitor is charged. When the capacitor is then connected to the bulb, no battery, and light turns on at its brightest and diminishes over time, eventually going out. At this time, the current is 0, and now the capacitor has discharged. For the 10 ohm light bulb, we found the charge time to be 8.1 seconds and the discharge time to be 9.9 seconds. And for the 20 ohm light bulb, we found the charge time to be 15.2 seconds and the discharge time to be 18.3 seconds. So it increased as resistance increased. Finally, we looked at RC circuit potential. We used the two equations above, which were equations for voltage decay, and if we plot the natural log of the voltage difference at time t divided by the voltage difference at time 0 versus time, the slope will equal negative 1 over RC. We did that to the right there with the circuit with the parameters listed below. So we found RC to be 5.981 seconds, and the calculated value that it should be is 0.2 farads times 30 ohms, which is 6 seconds. So they're pretty close. What if a real-life ammeter was used, not an ideal simulated ammeter? A real ammeter would not have resistance exactly equal to 0, so the current readings we would get would not be as accurate as the ones we got using the simulation, and they'd be smaller. What if a real battery was used to charge a real capacitor with no resistor in the circuit? The ideal model predicts the capacitor reaches full charge very quickly, but this would not happen in real life. Real wires have non-zero resistance, so this would increase the time it takes for the capacitor to be fully charged. So, doing these experiments in real life would introduce sources of error as described above.